Hello everyone and welcome to another part of the Galaga SDL tutorial videos. And in this video we're going to continue where we left off in the last video. So in the last video, let's run this project and see what it looked like. There we go. So what we had was an enemy coming in and then following the path up to here. So in this video, what we're going to do is to start from here and put it to where it should be within the formation. So as the enemies, more and more enemies spawn, they start to go to where they should be within the formation at the top. If it's a challenge stage. Otherwise, they just follow the path, and then once they finish the path, they are considered dead. So the first thing that we're going to need to do is to create a formation class to take care of the formation animation. So for example, when the enemies are still coming in, the formation translates over time to the right and then left. And once the formation is finished, so all the enemies are in and all the enemies are in formation, they start to spread apart and then come back together over time. It's kind of like a breathing animation. So let's get started first by creating that formation class. So in Galaga, add new item .h, and we'll make this one a formation.h. And then, if not defined, underscore formation underscore h. Define underscore formation underscore h. And then end if. So in this .h file, what we need to include is the game entity. So include GameEntity.h. We'll also include timer.h. Because we're doing translations, we're going to need the timer for that. And then we'll do using namespace quick SDL. Now to move on, we'll do a class formation, and this will inherit from our GameEntity class. This way we can assign the enemies once they're in formation to be children of that formation class. Now, moving on to our variables. So private, and the first private variable that we're going to need is the timer. So timer pointer mTimer, and then the variables for the two different types of animations. The first one being the translation, so left and right as long as the enemies are still spawning and flying in. So we'll do a float m offset amount. And this is how much it translates by each tick. Float m offset timer and float m offset delay. That's our usual timer setup. And then int m offset counter and int m offset direction. And the counter and the direction, the counter is because it translates 4 times or 8 times to the right, and then switches directions and translates 8 times to the left. So the counter is going to keep track of how many times it translated, so it's up to 8 times, and then flips the direction and then it starts translating to the other direction. So this will be it for our translations. Next up is the breathing animation. So this one will be a float, and we'll call this one spread offset, or spread timer, sorry. So spread timer, and then float m spread delay. So these are the two, timer and delay, normal thing that we always had. And then int m spread counter and int m spread direction. And that's the same idea as the counter and direction here. So now that we have all the variables that we need for our movements, we can have vector2 m grid size, and this will describe how far apart each enemy is from the enemies around it within the formation. And finally, boolean m locked. And as long as locked is false, that means enemies are still coming in, so we're doing the translation animation. And as soon as locked is true and the formation is right in the center, we can start the spread animation instead. Now for the public, we will have a few public functions. First one being the formation constructor and formation destructor, as well as a vector2 of our grid size, so that the enemies have an idea of where to go or where to be placed within the formation. And then end or void lock, which will lock the animation. So this is going to be called by the level. When the level figures out that all the enemies are inside their formation positions now, they can just lock the formation so that the breathing animation starts running. And then void update. And these will be all the functions that we need for now. So we can go ahead and make our CPP file. So we'll go to our Galaga source files and add new item. We'll call this one formation.cpp and include formation.age. So for our constructor, we'll do formation. Our mTimer is going to be equal to a timer instance. And for our values, so the first one will be the offset amount, and this can be anything for now. We can change it later. So our offset amount, let's say it's something like 30.0f, and then our offset delay, let's say 1.0f. So every second a tick happens, so it moves one tick to the left or right. And offset timer is going to start up being 0.0f. Our offset counter is going to start up being 4. And the reason why it's 4 is because the enemies are starting in the center. 0 would be all the way to the left or right. So right in the center would be 4, and that's why we're starting at 4. And then offset direction, and the direction is going to start up being 1, so it's going to be moving to the right. So this will be it for all these variables. Now for the spread timer. For this one, we will have spread timer is going to be equal to 0.0f. The spread delay will make it 1.0f as well, and we'll change it later. And then spread counter. The spread counter is going to start off being 0, and the spread direction is going to start off being 1. And 1 just means that it's spreading outwards, and then we can flip that to -1 so that it spreads, they come in together. And the spread counter is 0 because it hasn't moved yet, and then it increments up to 4 and then comes back in. So this will be it for all these variables. Now there are 2 more variables left, the grid size and locked. So locked is going to be false at the beginning. So mlocked is going to be equal to false. And our grid size is going to be equal to a vector2 of, and we can put any values that we want for now. So 50 and 80, for example. So this will be it, and we're going to be changing these values soon so that they fit whatever shape that we want the formation to make. So that if they are spread too far apart, we can lower the grid size. If the delay is too short or too long, we can change the offset delay so that the ticks happen faster or slower, and so on. And that will be it for the constructor. Now moving on to the destructor, formation destructor. We'll just say that our mTimer is equal to null. And that will be it for the destructor. Now to move on to our getter for the grid size, that'll just return grid size. So vector2 formation grid size, return grid size. So that will be it for that. And lock, all that would do is set lock to true. So void formation lock, and we'll say that mlocked equals true. And this will be it for that function. And finally, the update. And in the update for now, we're just going to add the translation animation, and then we're going to worry about the breathing animation afterwards. So void formation update. Okay, so when do we want to run the offset animation? So the translation. We want to run it as long as the formation is not locked yet. So if not mlocked, but we also need to keep it running until if it's locked. Even if it's locked, we need to keep it running until the formation is right back in the center once more, so that the breathing animation can start running. So we can say if it's not locked, or our offset counter is not equal to 4, because 4 is our centered position. we want to run the translation animation. So in here, we will increment our offset timer. So our m offset timer plus equals m timer delta time. And then if the offset timer is more than or equal to the offset delay, set the offset timer back to 0. And we need to translate one tick to the left or right. So we'll say our offset counter, m offset counter plus plus. So we increase the counter by 1 and translate by vector2, so vec2 underscore right multiplied by the offset direction, whichever direction that we're translating towards, multiplied by the offset amount. And this will be in world space. And that will be it for the translation. Now, to move on to check whether or not the counter is more than 8 or not. So if the offset counter is equal to 8, we need to flip the direction. So it starts off being 4, and then it's going to be 5, 6, 7, 8. So it's going to move 4 to the right. And then we're going to reset it to 0 and flip the direction. So it's 1, 2, 3, 4, 5, 6, 7, 8. And then flip the direction, set it to 0, and go on again. So m offset counter is going to be equal to 0. And the offset direction is going to be equal to -1. And that will be it for our update. And this will be it for our function formation class for now anyway, until we add the breathing animation as well. So we need to create an instance of this class in our level so we can pass it to our enemies. So in enemy, if we go to enemy, we can in here in enemy.h include formation.h, and now we have access to it in the level. So we can go to our level.h. So level.h, and all the way at the end, right before the enemy, what we can do is say formation pointer m formation. And then in level.cpp, we can create a new formation. So above enemy here as well, we will go and say that m formation is going to be equal to a new formation, and that's inside the constructor. So the constructor of the level. We'll say the formation is equal to a new formation, and the position of the formation, we want it centered in the play area. So m formation position is going to be equal to this bit right here. So where the start and the game over position are. So vector2, and that's in graphics. So for the X, it's screen width times 0.4, and for the Y, we'll put something like 300.0f, and we can change that later. So this will be it for our formation, and since we're creating it here, we can go down to the destructor right above enemy and say delete m formation, and m formation is going to be equal to null. And that will be it for now. What we probably need to do now is to update the formation. So to do this, we need to create a function for it in our level.h. So over here, what we'll do is to add a void. So void handle enemy formation. And so that's in level.h in a private function. We'll have handle enemy formation, and then we'll go down to, I think we had handle player death. So right underneath handle player death, we'll add level or void level handle enemy formation. And what this will do is say m formation update. So it'll just update the formation in here. And then we need to call handle enemy formation. So for that, we will go right here. So in the level update before the enemy update, we'll say m formation or handle enemy formation. And that will be it for our level.h and level.cpp. That pretty much takes care of everything that we need in here. So the last thing that we need to do is to make the enemies use that formation. So in our enemy.h, we will need to give it access to the formation. So the formation can be, well, it has to be a static through between all the enemies. So what we'll do is say static formation pointer as formation, and that's in our enemy.h. So right underneath as paths, we have our formation in here. And we will need access to the enemy states in the level, because we need to check whether the enemy is dead or not, and whether they're in formation state or not, and so on. So what we can do is to create a public area here, so public, and we will cut the states and put them in the public area instead. So now that we have access to those, we need a way to get our current state. So we'll make a getter function for that. So we'll go here, right above update, and put states current state, and this will return our current state. So we will go to our enemy.cpp and go all the way down right above update and say or enemy states enemy current state, and all this would do is just return current state. So that's right above the enemy update. We'll just add the current state right here. And that will be it for our public function. Now there are some changes that we need to do to the enemy class still. In the last video, I'm not exactly sure why I put all the handle functions as public, because these are not accessed from anywhere outside. We don't need them in here. So we can have a protected area. And in this protected area, we'll take all the handle functions, so the handle states, handle fly-in, formation, dive, and dead, and put them all inside our protected area. Now, we also need a way to set our state. So we will go down to the public area right above create paths and put in a static void set formation. And this will take a formation pointer and call it f. So now that we have this here, we can implement this function in our enemy.cpp. So we will go back to enemy.cpp, go here, and then initialize our S formation first. So we'll say formation pointer enemy S formation is going to start out being null. And then over here, right underneath create paths, we can say void enemy set formation pointer f, and our S formation is going to be equal to f. And that will be it for the static function and the static formation that we need. Now we can go back to our level and assign that formation that we created in the level. So we can go to level.cpp and go up to our constructor where we created our formation. And over here we can say enemy : set formation m formation. And now that we're setting the formation, every enemy that we create will have access to this formation, so its position and its translations, so that we can use that as the animation for the formation. Okay, so now that we have everything set up, we can start on some of the functionality for the fly-in. So now in enemy.h, we need to first add a few more variables in our private variable area. The first one will be an integer, mindex, and then a vector2, mtarget position, as well as a boolean mchallenge stage. And this will be it for the variables that we need. Now, this one will tell us whether it's a challenge stage or not, because if it's not a challenge stage, we don't want to go to a formation, we just want to go off screen following the path. And the target position is where you should go after the path is complete. Because we already have our Bezier curve going up to, let's say, the middle of the screen. We have a hook-looking path right now. And once we're there, we need to tell it in the target position where to go after that from to know where to go in the formation, or if it's a diving wasp, it goes towards the player instead. So now that we have these here, we need to give the enemy constructor access to the index and the challenge stage boolean. So in the enemy constructor, we'll add an int index. So int index, int path, and then a boolean challenge stage. And these are all the changes that we need to make for the constructor. Now we can go to our enemy.cpp and change the constructor to use these variables. So int index, int path, and boolean challenge stage. Now that we have these two variables being passed in, we can assign them. So mindex is going to be equal to index, and mChallenge stage is going to be equal to challenge stage. And that will be it for these variables. Now, the last thing that we need to do is to add a few extra functionality for the states that we're going through. For example, we need a function to fire as soon as the path is complete, and another function to fire when the enemy reaches its target position. So we will have, the first one will be virtual void, and this is in our enemy.h in the protected section. Virtual void path complete, and this will fire when our Bezier path is done. So now, as soon as the path is done, we can decide whether we're supposed to dive at the player or go to the formation position, and that's where we're going to be deciding that. And then next up is virtual void or virtual vector 2, and this one will be called fly in target position. And the fly in target position is the world position after the path is complete that you're going to. So it's going to be the formation position offset by the position within the formation that the object should be in. So now that we have this, we will also add a virtual void, and we'll call this one fly in complete. And flying complete is kind of like the path complete. Once this state is done and we reached our formation, we can either change to a formation state or set the enemy to dead if it's a challenge stage. So this will be it for these two. Now the last function that we need is going to be a pure virtual function, and this one will be called virtual void or virtual vector 2, and this one will be formation position equals 0. And the reason why this is a pure virtual function is because there's no way for the base enemy class to actually know where it needs to go, because the boss only has one row, the butterfly enemies have 2 rows each, and the wasps have 2 rows each. So these need to be decided in each corresponding class, not in the base class itself. And that's why we have it as a base, as a purely virtual function. Actually, we can change these two to pure virtual as well. So handle dive, we can set it to equal 0, and handle dead equals 0. Because the dive and the dead states are different for each enemy. Like the boss changes colors, and the dive state, each one of them, each enemy has a different dive animation and different dive path. So they're gonna be completely different. So now that we have all these declared here, what we can do is go to our enemy.cpp. So in enemy.cpp, the first one that we need to, now we're here creating an enemy. That's fine for now because we're gonna derive more classes from it, like the butterfly class and the wasp class. So it's just complaining because we have a pure virtual function in there. So where is our enemy.h? There we go. So the first function that we need to implement is our path complete. So in enemy.h, we will go down to right here, right underneath the constructor, and say void enemy path complete. Okay, so when the path is complete, if it's a challenging stage, then we don't need to go to the formation state. So, or we don't need to fly to where the formation should be. So what we can do is say if mChallenge stage set our current state to dead. And this will be it for this function. Next up is our fly and target position. This one will be void or vector2 enemy fly in target position, and the target position for the fly in will be our, so this one will be our formation position and then our target position within the formation. So this one will return S formation position plus our target position. And that will be it for this function. Now the third function that we need to implement is our flying complete. So void enemy flying complete. So when the fly-in is complete, we want to put our position, we want to put our position to be our fly-in target position, because translations are never exact, so it might overshoot it by a little bit. So we want to put it exactly where it should be in the formation, and that's what we're doing here. And we need to make it point straight upwards, and for that we'll just set our rotation to 0. Now next up, we need to set our parent to be the formation, and finally our current state to be the formation state. So whenever the fly-in is complete, this will be overwritten, by the way, in other classes. So the diving wasp will override this so that it doesn't put it in the formation, it dives at the player instead. But for most classes, it's gonna go to the formation state, so we might as well have it in here. It saves us a lot of time. And finally, the handle fly in state. So for this, we need to make a few changes. First one being, we need to go up here, and the current waypoint needs to actually be 1. And then the position needs to be at the current path at 0. And the reason for this is because I don't really think it through last time. Our waypoint is actually supposed to be our next waypoint we're going towards, not our current waypoint. So we need to start off being at the 0 waypoint and go towards the first waypoint. So these are the changes that we need to make here. And now in the handle fly-in state, what we can do is take our over here, we're setting our rotation, but instead of having this up here, we can cut it out and paste it right underneath here. So after the translation, we can increment our waypoint if it's close enough, and then keep going afterwards. And then there is one more thing that we need to do, is say that if the current waypoint is more than or equal to S paths at the current path dot size. So we're checking after we increment the waypoint that if we reach the last waypoint in the path, what we want to do is say that the path is now complete. So we're calling our path complete function. And that will be it for this part. Now here we're saying otherwise, what we want to do is to set the formation, set the current state to be equal to the formation. And this is not what we want to do. What we want to do instead is to fly to where the formation is, because before we were flying to the end of the path and stopping there. So instead of just stopping there, we want to continue to where we should be in the formation. So we will erase that, and then say that our vector2 dist is going to be equal to our fly-in target position minus our position. So our The flying target position is the world position we're going towards, and our current position, so that we can get the distance between the two. And then we're going to translate between our dist dot normalized multiplied by our m timer delta time multiplied by our m speed. And this all will be done in world space. And this will be it for the translation. Now, to set our rotation, we can just copy what we have in the rotation here and paste it there. So the a tan 2 dist y and dist x. And finally, we can say that if dist dot magnitude squared is less than epsilon, so if this happens, that means we reached our position in the formation. And we have a function that fires when this is complete, which is the flying complete function. So we can say fly-in complete. And that will be it for our changes in here. Now, in our handle formation state, we can go over here and say that our position inside the formation can be equal to our formation position. And you remember that this is our pure virtual function that we had in here. We will update it for each enemy separately. But this is what we're going to have for now. Now, since these two are purely virtual, we probably don't even need to have them here. So we can delete the handle delete state and handle dive state. We can delete these two. We don't need them anymore. And then we can go down to our rendering, and we don't really need to render the path anymore. So we can just remove the path for now. And that will be it for our enemy class for now. Now that we have all this set up, what we can do is to create our first enemy. And the first enemy will be the butterfly. So what we can do actually is here in M texture, instead of all this, we can set it to null. Because we don't want to load the texture. So in enemy.cpp in the enemy constructor, we can just set the texture to null because we want to load a different texture for each enemy. We just had this as a placeholder for now. And that should be it for this. Now we can create our butterfly enemy. So we can go over here in Galaga, add new item, .h, and we'll call this one butterfly.h. And in here, these enemy classes will be pretty short, if not defined, underscore butterfly underscore h, define underscore butterfly underscore h, and if, include enemy.h, and in here we will have class butterfly, which will inherit publicly from enemy. And then for our private functions, we will override a few private functions, and then we'll have our public functions. So the private functions that we want to override is, the first one will be our formation position, because this one is a pure virtual one and we need to override it. So we can go over here and say vector2 formation position, and then we will also have void handle dive state and void handle dead state. So now we have our handle dive state and handle dead state because they're both also pure virtual functions. And for our constructor, we can have butterfly int index, int path, and boolean challenge stage. So exactly the same as the enemy class. And then butterfly destructor. And that will be it for this class. Now we can create our CPP. And go down here, Galaga, add new, and .cpp, we can have butterfly and then include butterfly.h. And okay, in here we can do butterfly constructor. So butterfly, int index, int path, and boolean challenge stage. And this needs to initialize our enemy with these values, so index, path, and challenge stage. Okay, so now that we have these here, we can start off by first checking if it's a challenge stage or not. So if it's not a challenge stage, what we want to do is set our target position where is our target position? Right. These are all private. So in enemy.h, we need to change this private to protected. Okay, so in enemy.h, these need to be protected because we need access to all this in the new enemy classes. So target position is going to be equal to our formation position. And then our M texture is going to be equal to a new texture. This one, butterfly.png. And then we'll set the parent, so M texture parent is this, and M texture position is going to be vec2_0. And that will be it for the constructor. The destructor can be empty for now, so butterfly, or this butterfly destructor, and then vector2 butterfly formation position. Okay, so for our formation position, we're gonna create a vector2 called return value. So vector2 red val, and then we'll return red val. Now we need to set up our formation position, and for the butterflies, what they do is they come in, and let's say you spawn two, the first two go over here, and then the second two go over there. And then when you spawn another one, it goes here, and then here, and then here, and then there. So if we check the indices for these, this is 0, this is 1, this is 2, this is 3, 4, 5, 6, and 7. So what we want to do is to offset them by that amount if it's on the X or the Y, so that we know where they should be within the formation. So we can say that our red val dot X is going to be equal to, and what I have here for that is S formation grid size dot X, so whatever amount we want to offset by within the grid size, plus S formation grid size dot X times 2 times M index divided by 4. Okay, and that might seem a bit convoluted, but the main idea here is that it starts off by offsetting. Let's say our grid size is 30. So it starts off right from the middle where our formation position is, and then it offsets by 30 here or 30 there. And this is by, over here, we're gonna multiply all this by the power of -1 raised to m index modulus 2 plus 1. Okay, so the whole idea here is, let's say our index is 0. So when our index is 0, we have our index 0, modulus 2 is 0. Plus 1 is 1. So negative 1 raised to the 1 would give us a negative value, which would give us negative 1. So whenever the index is even, we're going to go to the left side. And this is what this section is doing right here. Because you'll notice here, this is 0, 2, 4, 6, 8, 10, and so on. This is 1, 3, 5, 7, 9, 11, and so on. So we want that as long as the index is even, we want it to give us a negative value. If it's odd, we want it to give us a positive value. And this is what this is doing right here. Now, what this is doing, on the other hand, is first, it's offsetting it by whatever the grid size is. So let's say the grid size is 30. It's starting off by offsetting the first one and the second one and so on by 30. And then after that, it's offsetting it by twice as much multiplied by the index divided by 4. Because this is 0, this is 1, this is 2, this is 3, and so on. And then 2 divided by 0 is 0. 6 divided by 4 is 1. And then it's going to be 8, so it's going to be 2, and so on. It might seem convoluted, but this is, once you wrap your head around it, it seems pretty straightforward. It's just that it gives us a way to set all the positions without specifically telling it where to go. So that's the x value. The y is a bit more straightforward than that. So redval.y is going to be equal to S formation grid size.y multiplied by 2 brackets m index modulus 4 divided by 2. And this will be it for this part. So m index, because over here what we have is, so we have our formation.y, so we either want it to be 0 or whatever the, so we want this value to either be 0 or 1. So what we have here is 0, 4, 0, 4, 8, and then 12, and so on. So this one, modulus 4 would give us a 0, divided by 2 would give us a 0. And then 1, 5, and so on. This modulus 4 would give us a 1, and then divided by 2 would give us a 0, and so on. So this one, this is just so that this, for all the stuff at the top, would give us a 0, and all of the stuff at the bottom would give us 1. And it's just multiplied by the offset on the y. And that will be it for this function. And that will be the most convoluted part of this video, I promise. Okay, now to move on to the easy bit, which is to just say butterfly handle dive state empty function void butterfly handle dead state empty function. And that should be it. Now we can create one of our butterflies and see how it behaves. So in our level, we can say m_enemy is a new butterfly. So we'll probably need to include that. So instead of enemy.h, we can include butterfly.h. So in level.h, we'll replace enemy.h by butterfly.h. And then in level.cpp, we'll make a new butterfly. The index will be 0. The path will be 0. And the challenge stage will be false. So let's try to run that, and hopefully it works. Let's see how many errors I made. Okay, no errors so far. Okay, so it's coming in. And there we go. It went into position and it's traveling left and right. So now we need to spawn all the butterflies and see what they look like. So I really hope that works. So in level, in enemy, instead of just a single enemy pointer, we'll make an std vector, and this will make it enemy pointer vector, and we'll call this one enemies. Now we'll make an integer above it, and we'll call this one, wonder why it's complaining. Oh, it's because I just put an int there. Okay, so int m butterfly count, and this will be how many butterflies we have spawned. So over here in level, we don't need this anymore, so we can remove the enemy and say our butterfly count is going to start off being 0. So this is in our constructor. We'll set our butterfly count to 0. And then we'll do in the destructor for int I equals 0, I is less than enemies dot size I plus plus, delete enemies at I, and then enemies at I equals null. And that will be it for here. Next up is the update and render. So in our update function, we'll just loop through it and update them. So for int I equals 0, I is less than enemies dot size I plus plus enemies at I update. And then we'll copy this and do the same thing in render, and we'll just say render instead of update. And that will be it for that. So let's try to run it and make sure that everything is working for now. Okay, so everything ran. Now we need a way to spawn an enemy. So what we can do is we can go to our level.h and add a private function to spawn enemies for us. So over here, we will make right above handle enemy formation, we'll put void handle enemy spawning. And for now, we'll make it so that you press a key to spawn an enemy. So in here, we can go down to right above handle enemy formation. Where did we put that one? So handle enemy formation is right here. So right above it, we can say void level handle enemy spawning. And for this one, we can say if input or if input manager instance key pressed, and this one will be SDL underscore scan code underscore, let's say S. So if S is pressed, and let's make it that only 16 butterflies are spawned. So M butterfly count is less than 16. So as long as the butterfly count is less than 16, we need to spawn a butterfly. So we're gonna say enemies dot pushback and new butterfly, and this will be, so its index will be its butterfly count. So index is going to be butterfly count. Its path is going to be 0 since we only have one path for now, and challenge stage is going to be equal to false. And that will be it for this part. So let's see what happens now. There we go. So if we press S, nothing happens because we haven't called that function. Okay, so we can go down to update, and right before handle enemy formation, we can handle enemy spawning. And that will be it. So let's run it. And you'll notice that we're working on this in some sort of module, so that when we have a file that has all the enemies that need to be spawned in the level, we can just load it, and instead of pressing S, for example, we'll just load it from the file. There we go. So if we press S, enemies are being spawned, but they're all going to the same place. So why is that? Well, that is pretty cool, but because we are not incrementing probably the butterfly count. So when we spawn a butterfly, we can say butterfly count plus plus. So now let's see if that works. So now pressing S, butterflies are coming in, and then they are putting themselves in the right place. It seems like the offset is the distances between the butterflies is way too big. So if we want to change that, all we need to do is to just go to the formation.cpp and change the grid size. So let's say the grid size will be 32 by 64. And let's see what that looks like. So that was in formation.cpp, and the constructor will just setting the grid size to 32 by 64. So that should give us more bunched up together enemies. There we go. That looks a lot better. But the offset amount is way too high. They're moving way too far to the left and right. So for the offset amount, we'll change that to 10. And the offset delay, we'll change it to 0.4 instead of 1 second. So that they're moving faster and they're moving in smaller intervals. So let's see what that looks like now. There we go. 3 enemies left. And for some reason they're just going off screen. That's interesting. So what did we miss here? Okay, so in our formation.cpp, let's check what we did over here in our update. So in the update here, we have it that if the offset timer is, so it's going to increment by delta time, the offset timer is equal to, it seems like offset counter plus plus, reset the offset counter and flip back to nothing. That's odd. Should be working. Okay, let's see what's going on. Oh, no. I have it. Why do I have it equals 1? Offset direction times equals 1. This needs to be times equals. I was just setting it to 1 and it's going to the left side. That's why. Okay, so in the formation.cpp update, we need to change the offset direction to times equals 1 so that it flips the direction every 8 ticks. That should work, I hope. There we go. And there we go. So they're moving to the left and right, and this is, it seems to be working pretty well. They seem to be too low though, so we will just go to our level.cpp where we're setting our formation position. So in our constructor in level.cpp, we have it set to 300 on the Y. We'll put it at like 150, and that should raise the entire formation upwards. There we go. Now we're spawning all the enemies. And okay, this seems to be working pretty well. Alright, so the last thing that we need to do now is to check when all the enemies are in place, we need to stop moving them to left and right. And for this, we are going to go down to our handle enemy formation. That's the one. And then here, what we want to do is to check if the enemies are all in formation or not. So we can say that if the butterfly count is equal to 16. Now that I think about it, maybe we should just have a const. So in level.h we'll have a const int max underscore butterflies equals 16. So we'll have max butterflies equals 16 and butterfly count equals 0. That way we don't need to write 16 everywhere. So now we can go back to our level.cpp and handle spawning as long as it's less than the max butterflies, and this one if the butterfly count is equal to the max butterflies. So if it's equal to that, what we need to do is check if all the butterflies reached the formation or not. For that we can do for int I equals 0, I is less than menemies.size, I++, and we need to check to make sure that none of the enemies are in the fly-in state. So right before the for loop we can put a boolean fly-in equals false, and if menemies at I current state is equal to enemy fly-in, so if any of the enemies is in the fly-in state, fly-in is going to be equal to true. And then all the way at the end we can say if not fly-in, so if not fly-in, that means if this is still false, that means none of the enemies are in the fly-in state and all the enemies already spawned, so they're all either dead or in the formation state, so we should stop translating. So mFormation log. So just log the formation once all the enemies have spawned. And once we add the wasps and the bosses, we can just add to that. So let's see what that looks like now. What is it complaining about? No global operator is found because I forgot the 2 brackets here. Okay. So now when I spawn all the enemies and put them in place, they should start moving. They should stop translating left and right. So pressing S 16 times, it should spawn all the enemies. They should go into place. And then once it's centered, they should all stop. There we go. And we can start the breathing animation. All right. So now that we have the butterflies, we might as well add the wasps as well. So over here, we will add a new item, .h. This one will be wasp. If not defined, wasp underscore h or underscore wasp underscore h. Define underscore wasp underscore h. And if. Same idea as the butterfly, so I'll probably just put this one here to copy and paste what I have here. Include enemy.h class wasp public enemy private and public. There we go. Okay, so for the wasp, what we need to do is to override a few functions in here as well. But for the wasp also can dive at the player at any time. So what we want to do is to have a private variable as well. So this one will be a boolean mDiver. So this one dives at the player when it's coming in. And then we will have a vector2 fly in target position and then void path complete, void fly in complete, a vector2 formation position, void handle dive state, and void handle dead state. And this will be all the functions that we need. Next up is the constructor, so wasp int index, int path, boolean challenge stage, and a boolean to tell it whether it's a diver or not. So we'll call this one diver. And then a destructor, so wasp destructor. And that will be it for the wasp.h. Now we can create our wasp.cpp. So Galaga, add new wasp.cpp, include wasp.h. And the wasp class is a little bit more complicated than the butterfly class, because the wasps also dive at the player when they're coming in. They don't just shoot a bullet or something at the player, they have a completely different behavior when they reach the end of the path. And that's why we're overriding the path complete and the flying complete functions in here. So what we need to do here is to first declare our constructor. So wasp, this one int index, int path, boolean challenge stage, and boolean diver. And then we will do enemy index path challenge stage, so that should be taken care of. And finally we can just do the same thing that we did before. If not challenge stage, we need to set our target position. So our target position is going to be equal to our formation position. Now we need to set mdiver to be equal to our diver boolean that we're passing in. And then we need to load our texture. So mTexture is going to be equal to a new texture, and we'll call this one wasp.png. And then mTexture parent is this, and mTexture position is going to be centered. So vec2_0. And that will be it for the constructor. For the destructor, there's not much to write there. So wasp. Okay, so for the fly-in target position, our fly-in target position will be vector2 wasp fly-in target position. If it's a diver, then the target position will return our target position. Otherwise, it's gonna run whatever the enemy's target position function is. So enemy fly target position. So if it's not a diver, it's gonna follow the formation position. Otherwise, it's gonna fly towards the target position. So that should be fine. Void wasp path complete. So for the path complete, at the end of the path, we need to get the target position that we need to fly to if it's a diver. So if it's a diver, let's make it fly towards, for now, we can say mTarget position is going to be vector2_0. So it's gonna fly to the top left of the screen, because we don't have access to the player's position yet. Else, so otherwise, we just need to run the path complete of the enemy. So else enemy path complete. Okay, and that should be it for our path complete function. Next up is our is gonna be our fly-in complete. So void wasp fly-in complete, and if it's a diver, if it's a diver and it reaches all the way to the end of its target position, because that's when flying complete fires, we just need to set its current state to dead. So mCurrent state is equal to dead. If it's not a diver, else we need to run the enemy's flying complete. So enemy flying complete. As you can see, the wasp, we're just overriding the section for the diver, and then if it's not a diver, we're just following the normal functionality of the enemy class. Now, the final function that's not virtual is the formation position, and it's going to be sort of as convoluted as the butterfly one, but we're just going to copy and paste what we have from before. So void wasp formation position, or vector2 actually, not void. Vector2 wasp formation position, and what we have here for the butterfly, there it is. We can just copy what we have from here, so all these 4 lines, and paste them here. The only difference between a wasp and a butterfly is where they are on the y-axis. So what we can do is offset it twice by the grid size. So we can do s formation grid size dot y multiplied by 2 plus. So this is the section that we need to add, and that's it. So go down 2 grid cells and then add whatever you had from before. And this will be it for this part. So now we can do void wasp handle dive state empty function, and void wasp handle dead state and another empty function. And that will be it for our wasp class. So what we can do is to try it out. So we'll go to level.h, include wasp.h. Now we don't need these in here, so we can just put them back here again. So we included wasp.h, and in level.cpp, inside our enemy spawning, we can say, oh, in level.h we can put a maximum number of wasps as well. So constant max underscore wasps is going to be equal to 20, and int m wasp count. So same idea as the butterflies, but the wasps, we have 20 of them. So when we're spawning a wasp, we can say if input manager instance key pressed, and we can say SDL underscore scan code, and for this one we'll make it D. So if D is pressed and m wasp count is less than the max wasps, we need to increment the wasp count, so wasp count plus plus, and m enemies dot pushback a new wasp of, and this one will be m wasp count for the index. The path is going to be 0, the challenge stage is false, and the diver will be false. So it's not a diver, we're spawning the wasp, and let's see if that works. So when we press D, we should get up to 20 wasps, and when we press S, we should get up to 16 butterflies. Right, so it couldn't load. Right, I did not add the wasp graphic. So we can open up the folder here in our debug assets, and I need a wasp. So I have a wasp here. There we go. So I have a wasp.png. It's just like the butterfly, and let's try it now and see. There are the wasps, there are the butterflies. The wasps go into their place, the butterflies go into the top, and the wasps at the bottom. and then they all stop. We're almost there. The last thing that we need is the boss. So we just need 4 bosses, and that's it. So we also need to say over here that if in the handle enemy formation, mwasp count is equal to, so this needs to be and mwasp count is equal to max wasps, so that we don't have wasps still flying in while the so we don't have wasps still flying in while the what am I trying to say here? Yeah, anyway, so now we need to implement the boss. So this has been a very long video. Add new item .h, and we'll make this one boss .h, and the boss is very small. So that will be if not defined underscore boss underscore h, define underscore boss underscore h, and if include enemy.h. What else did I have in here? Let's get the butterfly again on the side. Okay, so class boss public enemy, and the boss class is gonna follow pretty much the same outline as the butterfly. So just to save up on time, we can probably copy this entire class and paste it in here and change this one to boss, because they are pretty much identical. Okay, so the last thing that we need to do now is to change the constructor to boss and the destructor to boss. So now that we have these here, we can make the CPP file. So we'll go down here in Galaga, add new item, CPP, and we'll make this one boss. Include boss.h, and this will seem pretty familiar because it's pretty much the same stuff that we did from before. So we will have our boss int index, int path, and boolean challenge stage, enemy index, wait, what am I doing? Index, path, and challenge stage. There we go. All right, so we need to load up the texture. We'll say mTexture is going to be equal to a new texture. This one will be called boss.png. mTexture parent is going to be equal to this, and mTexture position is going to be vector2 underscore 0. So just enter it. Then our destructor, so boss, that can be empty, and then vector2 formation position as usual, formation position. And the boss's formation position is a little bit different than the butterfly and the wasp. So what we're going to do is to go to what we have in the wasp and well, I guess we can get the, where did the butterfly go? Butterfly.cpp. We can go get the return value, everything inside the formation position, and put it right in here. But instead of dividing it by 4 over here, all we need to do is to just divide the index by 2 instead. And that will be it. As for the y, instead of doing all this, we just need to go one grid size above the butterfly, which is negative. And that will be it for this function. And then void boss handle dive state, void boss handle dead state, and that will be it for the boss class. Now we can go to the level, include boss.h, and then we can say constant int max bosses, equals 4, and then int m boss count, now in level.cpp. Oh, right underneath butterfly count we can say m wasp count is equal to 0 and m boss count is equal to 0. That's what we were missing from before. Okay, so that should be it for those. We can go down here and spawn a few bosses. So if input manager instance key pressed is SDL underscore scan code, and we'll make this one F, and m boss count is less than the max. We can probably close this one now. Max underscore bosses. We can say m boss count plus plus and m enemies dot pushback and new boss, and this will be using boss count. So this one will be using boss count, as well as what do we have here, path 0 and challenge stage is false. So this will be it for this part, and then over here we need to also check if all the bosses were spawned. So and m boss count is equal to m or max bosses in our handle enemy formation. And this will be it. Oh, I didn't add the texture for the boss. So I can go over here and I have a boss texture right here. So that should be it for this one, and it's called boss.png. So F should spawn bosses, D should spawn wasps, and S should spawn butterflies. There are the butterflies, there are the wasps, and 4 bosses. And then the bosses should go all the way at the top. Something seemed off here. Why did the bosses just snap? Let's try it again. Let's see. So they're flying up to here and then snapping instead of going all the way up. So let's look through it and see what's going on here that's making it do that. So the grid position should be equal to what this here is multiplied by 2 and index divided by 2. So that seems to be fine. I wonder what the issue is. And that only happens for the boss, I believe. Let's try to run it again and see. Because these ones, so let's try the butterflies. I don't think they snap, no. The wasps, they don't snap either. No. So the boss snaps from here to there. So why is this the case? So return value will be equal to, right. Over here at in the boss constructor, we did not put what we have over here, the target position. So if not challenge stage, m target position is going to be equal to formation position. I think that was the case. Okay. So let's see now if the bosses go to where they should be. Yep. And yeah, so that should be all the enemies spawning and going to where they should be. And then once it's in the middle, they all stop. And now we have our enemy formation set. I think for the rest of the stuff that I wanted to add, which is the breathing animation and the wasp diving, I'll make it in another video because this video is getting ridiculously long. So I really hope that this video helped. If you have any suggestions, questions, or feedback, please leave them below. Otherwise, thank you very much for watching, and I will see you in the next video.